After studying this module, you shall be able to know what is chemoselectivity, identify the chemoselectivity in various oxidation, reduction and acylation reactions, calculate the chemoselectivity for a particular reaction, selectivity, which, where and how. Different selectivities we normally think about are chemoselectivity, where regioselectivity and how terms as stereoselectivity. What is chemoselectivity? Chemical reactions have preferential selectivity of one functional group over the other different functional groups and unequal reactivity of the one of the two identical functional groups. Such predictions based on connectivity are generally considered plausible, but the physical outcome of the actual reaction is ultimately dependent on the number of factors that are practically impossible to predict to any useful accuracy: solvent, atomic orbitals, etc. In another definition, if an organic compound contains more than one differential functional groups or more than one like functional groups that are non-equivalent, if a reagent reacts exclusively or predominantly with one of them, the reaction is said to be chemoselective. Different examples of chemoselective reactions. Chemoselectivity in reduction. Chemoselectivity in reduction of the carbonyl compounds. In general, a compound with single functional group like ketone, for example as shown here in the figure 2-hexanone, the carboxylic acid group can be reduced to alcohols 2-hexanol and 1-hexanol as shown here in the structures. We can see one being reduced to the OH group, which is shown by the figure by the use of a reducing agent, which is sodium borohydride. Acids again reduced to alcohols from 3 to 4. Reduction of an organic compound contain two groups, a keto and a carboxylic acid. By using a reducing agent gives three possible products: 5-hydroxyhexanoic acid, 6-hydroxyhexane 2-one and 1,5-hexane diol. As we can see that if only the keto group is reduced, we get a OH and an oic acid. If only the carboxylic acid group is reduced, we get a keto and an alcoholic group, and if both the groups are reduced, we get diol. As such, chemoselectivity can be difficult to predict that which of the group is being reduced, but observing selective outcomes in the cases where many reactions are plausible is common. Examples include the selective reduction of 5-oxohexanoic acid 5 with sodium borohydride and lithium aluminum hydride goes to the greater relative chemoselectivity and gives different products: 5-hydroxyhexanoic acid 6 and 1,5-hexane diol respectively. The solvent systems are different, and changing the reducing agents give us the two different products where each of the reagent is chemoselectively reducing one of the functional groups and not the other. Evidently, reduction of compound 5 by sodium borohydride reacts selectively with only keto group and gives 5-hydroxyhexanoic acid as chemoselective product, but lithium aluminum hydride reacts with both keto and carboxylic acid groups and gives 1,5-hexane diol. Thus, the reaction of 5-oxohexanoic acid with sodium borohydride is a chemoselective for reduction of ketone in the presence of a carboxylic acid. Chemoselective reduction of a double bond ene molecule over the carbonyl group. Reduction of alpha beta unsaturated cyclopentanone by using hydrogen palladium gives cyclopentanone. So, we can say that hydrogen palladium reacts with only the carbon-carbon double bond, which is the ene system. This reduction is selective for the carbon-carbon double bond. A similar case is also seen with the reduction of cyclopentanone, which is reduced to cyclopentanone. Chemoselective reduction of carbonyl over the C double bond C. Reduction of alpha beta unsaturated cyclopentanone in the presence of sodium chloride with sodium borohydride obtained alpha beta unsaturated cyclohexanol as the product. This reduction is selective for the carbonyl group, whereas the C double bond C or the ene group remains unaffected. Chemoselective reduction of alpha beta unsaturated ketones over the allylic alcohols. 4. 3-oxo-cyclohex-1-enyl butanol reacts with sodium borohydride, cerium chloride, ethanol at the temperature of -15 degrees to give 4,3-hydroxy-cyclohex-1-enyl butanol. Reducing agents like sodium borohydride in the presence of cerium chloride and ethanol reacts with only alpha beta unsaturated ketone. Another example is the reduction of alpha beta unsaturated ketone reacts with sodium borohydride, reduce the carbonyl group and gives the product 16, while BH3, 1/3 of the equivalent, gives the allylic alcohol 15 by the reduction of alpha beta unsaturated ketone. Both the reactions are depicted here in the figures, where sodium borohydride in the 0.25 equivalent amount reduces the carbonyl group to the alcohol, while the borohydride reduces the allylic carbonyl group in the reaction B. Chemoselective reduction of the alkenes over alkenones. Reduction of S2-methyl-5-prop-1-ene-2-yl cyclohex-2-enone reacts with the Wilkinson catalyst triphenylphosphine, rhodium chloride and hydrogen gives S5-isopropyl-2-methyl-cyclohex-2-enone by the selective reduction of the terminal alkene. So, we can say that this reduction methodology is selective for the terminal alkene over the substituted alkene. Reduction of S2-methyl-5-prop-1-ene-2-yl cyclohex-2-enone with K-selective THF gives 5S2-methyl-5-prop-1-ene-2-yl cyclohexanone as shown in the figure and the compound number 19. This reduction methodology is again selective for more substituted alkenes over the terminal alkenes. Chemoselective reduction of alkenones over the alkenes. As can be seen here, it is only the double bond which is in conjugation with the double bond O is being reduced, while the other double bond at the position outside the ring is not affected by this reaction. Chemoselective reduction of the alkynes over alkenes. Reduction of 1-but2-enyl 2-prop-enyl benzene in the presence of Lindlar catalyst, which is palladium calcium carbonate with quinoline by hydrogen to give 1-but2-enyl 2-prop-1-enyl benzene. This is an example of the selective syn addition of hydrogen to alkyne over the alkenes. Chemoselective reduction of the ester COOR over cyano group. Reduction of ester 22 in the presence of calcium borohydride to give 3-hydroxymethyl benzonitrile. It is only the ester group reduced to the alcohol while the cyano group remains ineffective. Chemoselective reduction of the carboxylic acids in the presence of esters. Reduction of tetrahydro 5-oxofuran 2-carboxylic acid in the presence of borane dimethyl sulfide complex to give dihydro 5-hydroxymethylfuran 2-one as shown here in the figure. Chemoselective reduction of the carbonyl over the ester. Reduction of methyl 4-acetyl benzoate in the presence of sodium borohydride in methanol to give methyl 4,1-hydroxyethyl benzoate. It is seen that the carbonyl group is reduced as in preference to the ester group with the presence of sodium borohydride and the methanol. Chemoselectivity in oxidation. Chemoselective oxidation of the allylic alcohols over the other alcohols. Oxidation of the allylic alcohols in the presence of the manganese dioxide and chloroform to give alpha beta unsaturated ketone. Manganese dioxide selectively oxidizes the allylic alcohol in the presence of the other hydroxyl groups as shown here in the figure where the selective oxidation of the allylic alcohol takes place. Chemoselective oxidation of the secondary alcohols over the primary alcohols. Oxidation of butane 1,3-diol in the presence of silver carbonate and silyte selectively oxidizes the secondary alcohol over the primary alcohol and gives 4-hydroxybutane 2-one. Chemoselective oxidation of lactols over other alcohols. Oxidation of tetrahydro 5-prop-1-enyl furan 2,3-diol in presence of silver carbonate and silyte to give selectively dihydro 3-hydroxy 5-prop-1-enyl furan 2,3-H-one. This methodology is selectively oxidize lactol in the presence of the other hydroxyl groups. Chemoselective epoxidation of allylic alcohols over the unfunctionalized alkenes. Epoxidation of 3,7-dimethyl octane 2,6-diene 1-ol in the presence of tertiary butyl hydrogen peroxide and vanadilyl acetyl acetonate to give 3-methyl 3,4-methyl pen-3-enyl oxyran 2-yl methanol. Chemoselective epoxidation of alpha beta unsaturated ketones over alkenes. Epoxidation of S 2-methyl-5-prop-1-ene 2-yl cyclohex-2-enone in the presence of the alkaline hydrogen peroxide gives 4S 1-methyl-4-prop-1-2-ene 2-yl 7-oxabicyclo-410 heptane 2-one as shown here in the figure. Chemoselective epoxidation of the alkenes over alpha beta unsaturated ketones. Epoxidation of 2-methyl-5-prop-1-ene 2-yl cyclohex-2-enone in the presence of meta CpBa to give S 2-methyl-5-R-2-methyl-oxyrane 2-yl cyclohex-2-enone 37 as shown here in the figure. So, it is the chemoselective reaction where only it is one of the group which is being affected by the given reagents. Acylation reaction. Chemoselective acylation of amines over phenols. Acylation of 4-aminophenol as depicted here in the figure 38 in the presence of acetic anhydride and pyridine to give N-acylated 4-aminophenol 39. In this reaction, N-acylated 4-aminophenol shown here in the figure 39 is obtained because the amine group is more nucleophilic than that of the phenol, and as a result it gets converted to an acylated derivative while the OH group does not. Chemoselective alkylation of the phenols over carboxylic acids. 4-hydroxybenzoic acid shown in the figure 40 is treated with the base, gives the product 41, and followed by the treatment with the iodocyclohexane in the presence of acid gives 4-cyclohexyloxybenzoic acid. How to calculate the chemoselectivity? Oxidation of styrene 43 in the presence of hydrogen peroxide to gives possible 4 products. Styrene oxide 44 is the major product as shown here in the figure. We can calculate the chemoselectivity for the formation of the styrene oxide. Various other isomers obtained and the other compounds obtained are in the different ratios of 10%, 5% and 10%, where major is the 80% of the epoxide which is obtained. Selectivity for the styrene oxide is calculated as per the styrene oxide as a ratio of the total products, which is 80 by 100 into 100, giving us the 80% of the product. To summarize, in this module we have taught you that if an organic compound contains more than one different functional groups or more than one like functional groups that are not equivalent, if a reagent reacts exclusively or predominantly with one of them, the reaction is said to be chemoselectively. We have thoroughly discussed chemoselectivity on various types of reactions like oxidation, reduction and acylation reactions. We have taught how to calculate the chemoselectivity for a particular reaction.